Hi there, in this video we are going to discuss and prove the fundamental theorem of calculus. So the fundamental theorem of calculus is the statement that binds together the process of differentiation and integration and establishes the direct relationship between the two, which makes it clear that differentiation and integration are inverse processes. Integration is the kind of inverse operation to differentiation in a sense. So to state the theorem, it can come in a couple of different versions, but the version we're going to state is we're going to let f of x be a continuous and differentiable function on an interval a to b. And let its derivative, we'll use the notation f prime x to refer to the derivative of f. Then what the fundamental theorem of calculus says is that if you integrate the derivative of f of x with respect to x and integrate it from a to b, then what you get is the original function f evaluated at b and a, and you take the difference of the two values like this. Okay, so inside here you can see we're differentiating f, and then we integrate the derivative of f, gets us the difference in values of f between the limits a and b. Now to prove this, we will use the linear approximation. Use the linear approximation with error formula, which says that if you evaluate a function f at value a plus h, what you get is the value of the function f at a plus h times the value of the derivative of f evaluated at a, and then you get an error term which is the form of h times epsilon h, where this error term has the feature that the epsilon h part still converges to 0 as h goes to 0. Okay, so this first part here is your linear approximation. And this second part here, the h epsilon h, is the overall error term. But the error term, even after you cancel off the factor h, the error term still goes to 0 as h goes to 0. So what we're going to do is we are going to evaluate the Riemann integral, use the Riemann definition for this integral here. Okay, and we're going to use the equally spaced partition. So for a given value of n, we'll use the equally spaced partition. X0 less than x1 less than x2, etc., etc., less than xn, where this endpoint xn is b, the first point x0 is the point a, and the intermediate points xi. The intermediate point xi is the previous point xi minus 1 plus an increment, and you take one nth, fraction 1/n of the distance between b and a, and that's for every value of I bigger than or equal to 1. So this is the equally spaced partition between a and b. So that would make the quantity xi to be equal to a plus excuse me, a plus I times this quantity. A plus I times the interval b minus a over n. So in the language of the Riemann integral, so the interval delta xi is always equal to b minus a over n. That's the increment we make, the width we make each of the small rectangles, and we'll use the start point, the left-handed limit, start point of each interval for the rectangle height. I.e. the language we had was xi star, which is it will be equal to xi minus 1. Remember, xi star is the point between xi minus 1 and xi, which we're going to use as the representative point for that interval to evaluate the integrand at that point to give you the height of the rectangle. So, applying the Riemann integral, we will get that I, the value of the integral, which is the integral from a to b. So we're integrating f prime x. We're integrating the derivative. Okay. So the definition of the Riemann integral is that we take the limit as n goes to infinity of the sum of the areas of all the rectangles. So this is going to be the sum from I equals 1 to n, and the height of each rectangle is f prime, the derivative, evaluated at the point xi star, times delta xi minus 1, which is the width of the ith rectangle. So we just want to develop this formula. So we're going to be taking the limit as n goes to infinity, and we put in our choices. So for xi star, we're using xi minus 1. And for delta xi, we're using b minus a over n. Every interval has the same width. And then we want to use this form here for xi minus 1. So this is going to be the limit as n goes to infinity. I probably should have wrote this in when I was writing the previous one. So for xi minus 1, we're using the explicit form for xi minus 1 in terms of a and b. So this is going to be a plus I minus 1 over n times b minus a. And then we still have b minus a over n multiplied by that. Okay, now we just want to pause here and just look carefully at what we're going to do next. We're going to be using our linear approximation with error result. Okay, so this linear approximation with error results, which I'll just highlight here in this red box, I want to apply that now to what I've got down here. Now, what do I have down here? Here I have the derivative of f, okay, which is located here in the linear approximation with error, and I'm evaluating it at a point a plus I minus 1 over n times b minus a. So we are going to consider this, I'll put it in blue, kind of the matching color, this expression here. No, let me think about it. That's not quite right. So this expression here, the b minus a over n, this is going to be my quantity h. And I'm going to think of all this quantity here as, now I'm going to write this down as a. Okay, I know it's not necessarily the same A as this, but this is going to be this A that's appearing up here, the base point in the linear approximation with error result. So what you see here is, what we're looking at here is an instance of this term here, right? Because I have the increment h multiplied by the evaluation of the derivative of f at this base point here. So the base point here is actually xi minus 1. Okay, so I can't just quite, I might zoom out a bit so I can just get them both, keep them both on the same board for a moment while I do the substitution. Okay, there we go. So I'm going to continue my expression here. The limit as n goes to infinity of the sum from I equals 1 up to n, but instead of this expression here, I'm going to substitute it using the linear approximation with error result. Okay, so what we're going to have here is we're going to have this term f of the appropriate a plus h minus f of a minus h epsilon h. What we're actually going to have here, so this is all under the scope of this summation here. I'm going to have f evaluated at a plus h. Okay, so a here is the term xi minus 1. But then we're going to add on one of the increments h to it. So I'm actually going to be looking at a plus I over n times b minus a. Okay, because I have a plus I minus 1 over n times b minus a, but then I add another b minus a over n to it. Okay, this a plus h term over here. Then I have minus f of a. So I have minus f of a, which is, and a is this expression here. So a plus I minus 1 over n times b minus a. F evaluated at that. And then I have the minus h epsilon h part. So this will be mine. Now the h is b minus a over n, and that's multiplying epsilon evaluated at that h, which is b minus a over n. And I need to close this bracket there. Okay. Sorry, I was obscuring some of that for a moment. So you might need to pause the video and just roll back and forward and just satisfy yourself about this substitution that we're doing here. Okay, so we were at this stage here. So f prime evaluated an argument times an increment h. So that's an instance of this term here from the linear approximation with error. So I'm going to replace each of these with the expression of the other things. F of a plus h minus f of a minus h epsilon h, which gives me this expression here. So I'll continue developing this now. Now it's worth just making some substitutions. This argument to the function f here, and note here now that we've now departed away from the derivative of the function f. We're now back to the original function f. This first term here, that's actually the number xi. Okay, and we have minus f, and this number here, if you look at the definition, that's xi minus 1. And I'll leave this as minus b minus a over n times epsilon b minus a over n. And just to emphasize it, this summation is summing all, is the summation governs this whole expression here. Now we can actually carry out this sum because a lot of the terms are going to cancel in there. Because each time you have a fxi, that will be cancelled by the following negative term, negative xi minus 1, when I has progressed to the value 1 bigger, So each positive term, f of xi, gets cancelled by the following negative term, negative f of xi minus 1, for the following value of xi. So almost all of these f's will cancel. The only ones that won't cancel is the first negative term, negative f of, which we'll call that x naught for the moment, because that has no earlier positive term to cancel with. And then the last positive term, f of xn, because that has no following negative term to cancel with. Okay, all the other evaluations of f here, they all cancel with each other, because for each positive one there's a partnering negative one which comes after it. And then we're adding up these terms. Now these terms, you'll notice, have no dependence on I. So this is the same term for each value of I. You're adding it up from I equals 1 to n, so you're going to get simply n times this. So what you'll get here is minus b minus a times epsilon b minus a over n. Epsilon evaluated there. These terms are just constants here because we have x0 is a, remember, and xn is always the end of the original integration interval. Xn is always b, and we got minus b minus a over epsilon b minus a over n. And now we can just take this limit exactly. These two terms are just constants, so we get f of b minus f of a. Here I'll just reorder it that way because that's the way it's quoted in the result. And then we've got the limit of this term, but this is the limit of this error, this factor from the original error term, epsilon evaluated at this. And all we need to note here is that as n goes to infinity, b minus a goes to, as n goes to infinity, b minus a over n goes to 0. And so epsilon of b minus a over n will go to 0 also. Okay, because remember, if you scroll back, the property that this error function epsilon has is that it goes to 0 as its argument goes to 0. So here we have it here, evaluated at b minus a over n, but as n goes to infinity, the quantity b minus a over n goes to 0, because it's just this fixed constant b minus a divided by n. So that's going to 0, and so the epsilon term goes to 0 as well. And so we're left with just f of b minus f of a, which is exactly what the theorem claimed, that the integral from a to b of the derivative of the function is indeed equal to this difference in the evaluations of the function f of b minus f of a. So this fundamental theorem of calculus is very important. Let me just zoom out a bit, try and get it all on the same page there, just to, as we make some of our closing comments. This is quite important. It establishes the rigorous link between the two processes, the process of differentiation and integration as well. So we're going to keep that strongly in mind, and we're going to be able to use and exploit the properties that we have already about differentiation, and we're going to be able to explore their consequences for the process of integration. So I'll be doing that with you in the upcoming videos and live sessions as well. Okay, see you soon.